Okay, in this lesson, lesson 10.4, we are going to be using a couple different kinds of graphs to compare populations. And the first type of graph we're going to be using is called a box plot. So here's a little informational blurb about box plots. A box plot uses a number line to show the distribution of a set of data. It divides the set of data into 4 parts using the median and the quartiles. Remember the Q1 and Q3 that we dealt with in lesson 10.2. A box is drawn around the quartile values, and whiskers extend from each quartile to the minimum and maximum values that are not outliers. And I'll give you an example of that here in just a second. A double box plot consists of 2 box plots graphed on the same number line, and that's really helpful for them to be just right, one above and one below the other, so you can easily compare the 2 sets of data or the 2 populations. You can draw inferences about 2 populations in a double box plot by comparing their centers, and that could be median. For the box plots, it's going to be the median. If we have another kind of graph, we can actually get the mean. And then we'll also compare the variability, or how different the numbers are as a whole set of numbers. Let's take a quick little look at what a box plot might look like. How these are going to work is we are going to have a number line, and somewhere along in the way here we are going to have whatever the median end up being. So let's say we had the median was at 50. What that's going to look like on the graph is that's going to be a mark inside this box that's mentioned. So let's say this was the median, and let's say way down here at 20 is Q1, and then up here at 60 is Q3. So then what that's going to look like is you're going to have a box that goes from Q1 to Q3 with a mark at the median. And then the low number, which has got to be something lower than 20, let's say it's down here at 0, there's going to be a dot there, and then a whisker. That whisker that it's talking about there is just a line segment from the edge of the box. And then let's say the, so this would be the low number, and then let's say the high number was just at 70. And I have a whisker going out there. And this would be a box plot. Sometimes these are called box and whisker plots. Here's the key thing though. There's just 5 numbers being shown here. There's the low value, which is this dot. There's the Q1, or first quartile, is the left side of the box. The bar inside the box is the median. The right side of the box is your Q3. And then the high value is the end of the whisker on the right hand side of the box. Now it says that there are not outliers. If there's an outlier in the mix, that is represented by an asterisk. So if we look at it, this box here is 40 long. The length of this box from here to here is that interquartile range that we talked about, because it's Q3 and Q1, how far apart they are. Well, it looks like they're 40 apart. So if we go the length of this from here to here is the interquartile range. So I can easily figure out what the interquartile range is without doing much work at all. It's the length of the box. In this case, it'd be 60 minus 20, or 40. So the interquartile range of 40, I can use that little 1.5 rule that we used in 10-2 to determine if there's an outlier. But on the graph, an outlier would be marked with a little asterisk. So let's say there was some crazy high number way out here. I'd replace that with an asterisk, and the next highest number would be considered the high number. This would be an outlier. When there are outliers, it makes it kind of tough to predict. We're going to get crazy values sometimes. So here's the idea of this. This is showing me how the data is distributed. The fact that this whisker is really short, but this part of the box is much wider, this means this 1/4 or 25% of the data is more spread out than the top 25% or 1/4 of the data. So think wider is more spread out. So something being wider equals more spread out. So when you look at a box plot, if something appears really, really short and narrow, that means it doesn't mean that there's nothing there. It means a lot of stuff is crammed in really close together. So a really short part of the box or a short whisker means a bunch of data is piled in real close together. So if it's really narrow, that means packed in data. We have lots of data packed in right there. So this short whisker means there's a lot of data piled in right there. 25% of the data is piled in between 60 and 70 there. And then 25% of the data is between 50 and 60. 25% of the data is spread out between 20 and 50 in this example. And then 25% of the data is spread out between 0 and 20. So that's kind of what box plots are going to look like. And then we're going to be having like 2 of them. A double box plot, and we're going to be able to compare the 2. So let's take a look at some examples of that real quick. So here is the first example 1, and let's see what we have here. Casey surveyed a group of students in her science class and in her math class. So the top one's her math class, the bottom one is the science class. The double box plot shows the results. Compare their centers and variations. Write an inference you can draw. So an inference, like a prediction or an educated guess of what is going on here. So this is worked out, but let's take a look at it. I want you to see how easy it is to get data from here. So first we want to compare the centers. With this type of a graph, I don't know individual numbers in here. I know there's a bunch of data in here, but I don't know what they are individually. So I can't do mean at all. I can't see repeat, so I can't do mode. The only measure of center that we can actually do is the median, and I don't have to do any calculating. It's sitting right here for me. It's already marked. This bar right here is the median. So this median is at 10. Whereas the median for the science class is at 20. So we can see the median is super easy. For the math class, it's this 10, and for the science class, it's 20. And how many times have you posted a blog this month? Oh yeah. So we can tell from that the science class in general posts more to the blog, about twice as much. And you can see that here. The median for the science class is twice the median for the math class. And that's just because 20 is twice 10. That's easy to compare. We can also see the overall range is the same. For the math class, it's from 0 to 30, and for the science class, it's 0 to 30. The ranges are both 30. So then we can go to interquartile range. But again, that's pretty darn easy because this is Q1 and this is Q3 for the math class. So it goes from 5 to 20. So 20 minus 5 is 15. This box is 15 long. The length of the box is the interquartile range. So this is the interquartile range for the science class, or for math class. For the science class, it goes from 15 to 25 here. For the science class, this is only 10. So the interquartile range is only 10 for the science class. So what that means, interquartile range is a measure of variability. The fact that the math class is 15 compared to the science is 10, it means the data is more spread out in the math class. Even though the overall ranges are the same, the middle 50% of the data for the math class is more spread out because it has a higher interquartile range. So I didn't have to hardly do any calculations there at all. I mean, this was just mental arithmetic, really. I can tell a lot from the graphs if I understand what the individual pieces mean in these things. So let's take a look at another one and we will discuss it. I guess before I do, I'll make sure I mentioned everything. Overall, the science students posted more because science, the median's at 20. The median of the math class is at 10. The median for the science class is twice. There we go. And there's a greater spread of data around the median for the math class because the box is wider. That's easy to tell. I can tell this box is wider than that one. The fact that they're both on the same number line makes it easy to do that comparison. So here is got it, number 1. And it says the double box plot shows the cost of MP3 players at 2 different stores. Compare the centers and variability of the 2 populations. Write an inference you can draw about the 2 populations. So if we look at it, let's compare the centers first. So the centers, the only measure of center that we can get from a box plot is the median. The median for electronics world is 70. So this is at 70 because it's above the 70. And the median for the bargain basement is at 60. So this is at 60. The fact that the median at electronics world is 70 and then for the median at bargain basement it's 60, I can safely say that the MP3 players at electronics world are more expensive on average because their median is $10 more. So the median for the electronics world, so if I compare the medians for electronics world, it's 70. I don't have to do any calculations. That bar there in the box tells me that it's 70. And for bargain basement, it is 60. So I could say, hey, MP3 players at bargain basement are cheaper. Or I could say MP3 players at electronics world are more expensive. Now we can see there are some at bargain basement that are more expensive than some of them at electronics world, but the overall population of MP3 players are more expensive at electronics world. So now we can do the variability, the interquartile range. This electronics world looks like this is humongous range here. But there could be just one MP3 player that is $100 and the next one is way down here. So using the overall range is somewhat deceiving possibly. So the interquartile range eliminates the possibility of some crazy number in the mix. So for electronics world, the interquartile range is the length of the box. It's from Q1 65 to 75, that is 10. And then for bargain basement, the length of this box is 55 to 65, that's also 10. So what that means is the prices of MP3 players around the median are spread out the same. So the variability of the prices is pretty much the same, but we can tell that the average of the median MP3 player at electronics world is more expensive. It should be also just visually, this graph is shifted to the right. Further to the right is greater prices. That's pretty easy to tell from that graph. So the medians are telling me on average, electronics world's more expensive, bargain basement's cheaper. The interquartile range, them being the same, means the spread of the data is the same. So they're both somewhat equivalent in how they're spread out. Now, if we use the overall range, we could actually do that. The only problem with that is this might not be but one MP3 player and everything else is way cheaper. So we don't really know about that. But if we did the overall range, that is from here all the way to here. That would be 55 to 100. The overall range is 45. for Electronics World. For Bargain Basement, it goes from 50 to 80, so it's only 30. So based on the range, I would say that Bargain Basement, there's less variability. There's only a $30 range. But again, that could be misleading because we don't know individual prices. If the next most expensive MP3 player Electronics World was 80, then the range would have been less than the range for Bargain Basement. It could be just one thing causing that. We don't know because we don't know the individual prices here. So that is got it number 1. So let's move on. For the next type of plot we're going to look at is a line plot, and another name for line plot is a dot plot. Now to me that seems kind of ridiculous that line plot and dot plot are the same thing. Yeah, a line plot, I guess you could use different symbols and dots. You use little dots, but what these look like are number lines where, like, if I have an 18 and 2 students scored an 18, then I put 2 little dots. But I could actually use any symbols I want. Like I could use little apples to show they're bringing apples to the teacher to get those good grades or whatever. And then a 19, if nobody got a 19, then nothing would be above the 19. And then 20, if 3 people got a 20, then I would do that. If you're making one of these, you should try very hard to get the dots to be nice and in line. That way, if a stack of dots is 3, it should appear to be taller than the stack of dots that's only 2. If a stack is, like if I did at 21, if I did something like this and put 3 little dots real close to one another, it would look the same height as other. That's not, you don't want to do that sort of stuff. You want to have equally spaced, nice, evenly spaced dots so we can see actually individual numbers here. Now this sort of a plot, we can see how things are distributed, but I can actually get individual numbers. So if we can get actual numbers, then we can do mean, and we can do even that mean absolute deviation that 10.3 was about. We can do a lot more work with this sort of a plot. It does involve doing some calculations, but with a box plot, I can't do things that involve adding up individual numbers because I can't see them. But on this type of a dot plot or a line plot, this is an 18, this is an 18, a 20, a 20, a 20, 21, 21. I can actually see individual numbers. So when we do this sort of a calculation, we can still do median, but we can add in mean as well. And then nicely enough, the tallest stack of dots is the mode. So that'll be pretty easy to do. Let's take a look at an example that's kind of worked out for us here. So this is example 2 from the notes file. So here we go, the double dot plot. So here we have a dot plot, here we have another one, but they are using the same number line. So even though there aren't any numbering up here, it's the same as what's down here. So it shows the daily high temperatures for 2 cities for 13 days. So this 13 right here, that should be how many dots there are. There should be 13 dots. Compare the centers and variations of the 2 populations. Write an inference you can draw about the 2 populations. Well, just instant glancing, which one looks like it'd be hotter? Well, Lake City's dots are further to the right than Springfield. Now, there's something super nice about both of these sets of data. And what's nice about them is if you look at the center of it, they are perfectly balanced on either side. And if that is the case, that's called being symmetric. So if it is symmetric, then we can do some really nice stuff with very little effort. We can do easy calculations because it is so wonderful that the top part of the dots is the same as the bottom part. And if we look at it, Lake City is the same way. So if we look at it, there's 3 dots in the middle, and then 2, 2, and 1, 2, 2, and 1. The same thing for Springfield. So it looks like I could just take this blob of dots and just shift it to the right, and I could get it to look exactly like that. The fact that they are both symmetric wonderfully like that tells us stuff. So let's take kind of look at it there. Just making sure I was writing there. If we look at it, the tall middle part of it here, this middle part of the data, this would be the median of it, because there's the same number above and below. But since it's symmetric, it's also the mean. So this middle part right here is the median, but it's also the mean. It's only the mean when it's symmetric like that. If it's not symmetric, you have to actually calculate the mean, but since it's nice and symmetric, I don't need to do that. That's awesome that I don't have to add these up at all. And if you think about it, the middle of this Lake City one is right here. This, for Lake City, is the median and the mean as well. So based on the median and the mean, what can we say? Well, this is at 81, Lake City's at 84. I could say that Lake City is warmer by about 3 degrees on average. I could use the mean or median. They're the same number here if it's symmetric. Now, if we look over here at this little most appropriate thing, to compare the centers and variations when both sets of data are symmetric, use the mean and the mean absolute deviation. So I could use interquartile range, but if it's symmetric, they recommend that we use the mean absolute deviation. Both of them being symmetric, I'm going to use mean. It's the same as median in this particular nice symmetric thing. But I'm going to use mean and then mean absolute deviation. However, I can do this pretty darn easily without doing a bunch of messy calculations. So I'm going to use the means. So the mean for Springfield is at 81, and the mean for Lake City, the mean is 84. So based just on that, I can say, hey, it's warmer in Lake City by 3 degrees. But then the interquartile range, we're not going to mess with that one because of this little recommendation here. I'm going to use the mean absolute deviation. So I'm going to do the mean absolute deviation, but let's take a look at it. If here is my mean, all of these dots, these three are 0 away from it. Well, how far is that dot away, and that dot away, and that dot away, and that dot away? We have 4 dots that are 1 away from this. So to do the mean absolute deviation, I'm going to have 4 dots that are 1 away, and then I'm going to have 1, 2, 3, 4 dots that are 2 away. So I'm going to have a bunch of 2's, and I'm going to have 4 of those. And then I have a single dot that is 3 away, and then a single dot that is 3 away. So I have 2 3's. Now here's the only trick. When I divide here, I'm not going to divide by how many of these numbers. I'm going to divide by how many dots. I didn't bother putting the 0, 0, and 0 in there, but those are numbers in the data. There are 13 days, so I'm going to be dividing that by 13 to do the mean absolute deviation, and this is for Springfield. So if I do that, I can do that arithmetic in my head. 1, 1, 1, there's 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 and 6 is 18. So the mean absolute deviation for Springfield is 18 over 13. And so 18 divided by 13, and I get 1.38 approximately. And it says rounded to the 10th. So that's why they got 1.4 there. I didn't round appropriately. Yeah, approximately 1.4. Well, you get the same thing for Lake City, and it should make sense to you because these little arrows that I did here, there's 4 that are 1 away. There's 4 that are 2 away, and there's 2 that are 3 away. They're exact same as before. So based on the mean absolute deviations, the spread of the data is the same. However, Lake City's warmer by 3 degrees. So overall, Lake City had warmer. Yeah, okay, there we go. I could tell that just because the dots were shifted to the right. So you will do mean and mean absolute deviation only if they are both symmetric. If they are not both symmetric, when neither set is symmetric or only one is, you're going to use the median and interquartile range. So you need to maybe jot that down. If they are both symmetric, you're going to use mean and mean absolute deviation. If they're not both symmetric, so if they're not both symmetric, you're going to use the median and then the interquartile range. So we'll have to actually list out some numbers and stuff to do that. So this kind of shows you what work you're going to be doing. So first thing you need to do is determine, are they both symmetric or not? And then that determines what arithmetic you're going to be doing. So let's take a look at an example that's not worked out for us and work through it. So first, let's read the problem, see what we got here. Got it, number 2. The double dot plot shows the number of new emails in each of Pedro and Annika's inboxes for 16 days. Hey, it's important. 16 days, 16 dots. There we go. Use the dot plots to compare the centers and variations of the 2 populations. Write an inference you can draw about the 2 populations. Well, just glancing at it, if I squint my eyes from far away and just said, hey, which one has dots that are further to the right, I think I can look at it. Yeah, it looks like Pedro's dots are in general more to the right. If I look at it, Annika does have a 38 and Pedro doesn't, but overall it looks like Pedro's dots are to the right. So I would say that should be true. It looks like it is, and that's what we'll see when we do the arithmetic. We need to know which center to use. So are they symmetric? Does Pedro's look symmetric and balanced? Does Annika's look symmetric and balanced? And the answer to both those are no. Neither one of them looks symmetric. So if they are not symmetric, if they aren't both symmetric, I'll stick that in there. If they are not both symmetric, then you are going to do the median and then do the interquartile range. Now, do we have to list all these numbers out? Well, we know there are 16 dots here. I can count them up, but it actually tells me that there's 16. So if there are 16 dots, the median is between the 8th and the 9th one. So the median is going to be between the 8th and the 9th dot. So let's use that fact here. 1, 2, 3, 4, 5, 6, 7, 8. The 8th one is right there, and then these are the top half. So where would this 8th one be? It would be at 35. So the 8th one is right here. This is the 8th one. This is the 9th one, and it's at 36. So the median is halfway between those two. So if I think about what's halfway between 35 and 36, well, for Pedro, the median is halfway between 35 and 36, so it's going to be 35.5. It's halfway between a 35 and a 36. So if I wanted to, I could do 35 plus 36 and divide that by 2, but I should be able to figure that out. It's just halfway between 35 and 36. So let's do the same thing for Annika. For Annika, we have 16 dots as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The 8th and the 9th one are right here. They're both at 32. So for Annika, the median is 32. I hope I don't need to do 32 plus 32 and divide that by 2. It's halfway between a 32 and a 32. So based on the median, the center is the median when they're not both symmetric. So based on that, it holds true that Pedro is getting more emails on the inbox on average. He's getting 35 and a half per day, and Annika's only getting 32. So now that we have compared the centers, Pedro's getting more. There's an inference. It looks like Pedro's getting some more email. Not every day necessarily, but on average. So now let's talk about the variation. The variation I'm going to do is the interquartile range. Interquartile range. So let's think about it. There are 16 numbers. If there's 16 numbers, we chop the data in half. There's 8 numbers on either side. But to get the interquartile range, I need to chop this data in half and this data in half. So I need 4 numbers in each of these blocks. So this Q1 is between the 4th and 5th number. There's 12 numbers to here. So this is between the 12th number and the 13th number. I could actually list them all out. I could do 30, 32, 32, 33, 34, 34, 35, 35. I could do that. But I'm going to use this idea that if there's 16 numbers, the quartiles are chopping the data up into 4 groups of 4. So after the 4th number, the Q1 is between the 4th and the 5th number. This median was between the 8th and the 9th number. And so this Q3 will be between the 12th and the 13th. And that'll be true for both sets of data here. So let's mark it on here. Let's go to blue. 1, 2, 3, 4, and then Q1 is between the 4th dot and the 5th dot, and that happens to be at 34. So this is Q1. This is Q1. Between the 12th and the 13th is Q3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So the Q3 is halfway between 36 and 37. So this right here is your Q3. So Q1 is at 34 and Q3 is at 36 and a half. So for Pedro, the interquartile range is 36.5 minus the 34. It is from here to here because I went between the 4th and the 5th and between the 12th and the 13th. And what is that? 2.5. For Annika, I'm going to do the exact same thing. For Annika, I'm going to count over. So let me erase that mark. 1, 2, 3, 4. For the interquartile range, the 4th one's here, the 5th one's there, so that's at 31. And then 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh, we had an extra dot in there. Interesting. I think there's a typo in this problem. It said 16 days, but there's actually 17 dots here. Interesting. So if there's a mess up in this problem, but if we go between the 12th and the 13th, it's going to be here to here. It's going to be a 34. I don't like this problem because it said there were 16 days, but there's not 16 dots here. There's more dots. There's 17 dots. So really that messes up my 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, it didn't mess up the median. The median's still there. But then 1, 2, 3, 4. They would move this to a 35 technically. And so that's a 4. The interquartile range for Anika's is more than for Pedro. Its interquartile range is 4 compared to 2.5. So in general, Anika's are more spread out, and that looks to be the case, even though they messed up and put 17 dots for 16 days. The dots for Anika are more spread out. Visually, that's true, but the interquartile range is saying that that's true as well. 4 is bigger than 2.5. So, quick inferences, Pedro, in general, gets more emails in his inbox. 35.5 is bigger than 32. And in general, Anika's, there's more variability in the number of emails that she has in her inbox because of the interquartile range being bigger than for Pedro's. So let's move on to the next example here. For example 3, we're looking at a double box plot. For this sort of a graph, we can't see individual numbers. So that's bad, and oh darn, I can't see the individual numbers, but it's good in that if you can't do individual numbers, then you can't do mean. The only thing you can do is median, and the median is this bar in the box and the bar in the box. And you remember what that little thing means? Yeah, if there's a crazy number in the mix, this is an outlier. So this is considered the high number because this is so crazy. It's thrown out as an outlier. So we're going to compare the medians. We're asked to compare the centers. The only center I can get from a box plot is the median. I can't get mean because I don't know individual numbers. I can't get mode because I don't know the repeats because I don't know the individual numbers. The variation I'm going to use is the length of the box, which is the interquartile range. So the first thing I'm going to compare the medians. So do that first. That's easy. It's this to this. Bar inside the box to bar inside the box. And they did that first. There it is right there. Hey, for Treetop Tours, the median's more. So quick deal. Zip Adventures doesn't have as many daily participants on average. Treetop Tours has more. So greater number of daily participants. I can easily tell that for the medians because 70 is bigger than 50. Not a brain buster there. So after you do the medians, then you're going to the second thing you're going to do is do the interquartile ranges. But remember, that's just the length of the box. Don't make that a complicated thing. This box is from 50 to 80. So this is 80 minus 50. The interquartile range is 30. 80 minus 50. 80 minus 50. For Zip Adventures, it's only 20 because look, from here to here, from 40 to 60 is 20. I would do 60 minus 40 to get that 20. So based off that, Treetop Tours is more spread out because the interquartile range is bigger. We can also see there's an outlier. So from the perspective of choosing where to go, if I was going to go to one of these, I don't want to have to wait. And I'd like it to have more of an idea of how busy it's going to be. If you look at the Treetop Tour one, it might be insanely busy, or it might be hardly anybody there. We don't know. The fact that this is really spread out means it's not very predictable. I want it to be predictable, so I know whether I go there or not. If I want a really busy one, this might be it, or it might not. I don't know. The Treetop Tour is very unpredictable because it's not consistent. Zip Adventures, the fact that its interquartile range is smaller, and the fact that it's nice and evenly distributed here. Look, this whisker, this side of the box, this side of the box, and this side of and this whisker are all the same length. That makes it more predictable. So evenly distributed, or at least as far as I can tell. We can't tell if it's perfectly symmetric because we don't know individual numbers, but the box plot looks nice and even. That is predictable. I have a better chance of guessing how many people are going to be there than this crazy spread out situation. So let's look at an example and work it out here. So this is got it number 3. The double dot plot shows Kareem's and Martin's race times for different 3-mile races. Compare the centers and variations of the two populations. Which runner is more likely to run a faster race? If we kind of look at it, Kareem's is nice. If you look at it, Kareem's nice and symmetric. However, Martin's isn't. Martin's goes up, down, up, not symmetric at all. So if they are not both symmetric, then you're going to do median and interquartile range. Those are the two you do. So for the center, you do the median, and for the variability, you do interquartile range. The median for Kareem is really easy because it's symmetric. This middle part is the median because look, there's the same number of dots on either side of it. So for Kareem, the median, Kareem's median is really easy to do. It is that 18 because these 4 dots in the middle of his dot plot is 18. Now for Martin, on the other hand, since it's not symmetric, we have to do some little counting over. So for Martin, let's see, how many dots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dots. If there are 15 dots, if I have 15 dots and I go to the middle, there's going to be 1 in the middle. And then there's going to be 7 here with 1 in the middle. That'll make the 15. So this will be the 8th number over. Does that make sense? The first 7 are on below it. The last 7 are after it. And then there's 1 in the middle. The 8th number, or the 8th dot, will be the median. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. This right here is the median, and it's at 17. So what do we know based on the median? On average, Kareem's time is longer. It's 18 minutes compared to 17 minutes. So which runner is more likely to run a faster race? It looks like Martin's. Now we have the issue of it's not as predictable for Martin because it's all over the place, but based on the median, Martin runs faster because he has a lower time. Now let's talk about variations. We're going to do interquartile range. Interquartile range, we need to know how many dots there are. So for Martin, there's 15 dots. For Kareem, there's 1, 2, 3, 4, 5, 10, there's 14 dots. So for Kareem, we have 7 and 7, and then in the bottom of this 7, I'm going to have the 4th number. So we're going to have 3 numbers The fourth number will be Q1, and then 3 more numbers. The median is between this, we know it's right here, but there's 7 dots. And here, I'll erase it and kind of show it here. Oop, erase it. So 1, 2, 3, 4, 5, 6, 7. The median is right there. It's between those two. So we have 7 dots on the low side of that median, and then 7 dots on the high side of it. 1, 2, 3, 4. This is your Q1 right there. There's 3 dots, Q1, 3 more dots. 3 dots, Q3, 3 more dots. So this right here is Q1, and this right here is Q3. So Q1 is at 17, and Q3 is at 19. So for Kareem, the interquartile range is 19 minus 17, it's 2. For Martin, we're going to have to we got to figure it out here. I want to erase that. I kept clicking it and it didn't do it. So we have 15 numbers. So the 8th number was the median, so I erased that, but now I actually want to put it back. 1, 2, 3, 4, 5, 6, 7, 8. This is the median. And then there are 7 numbers. Yeah, I have it right here. 7 numbers. So if we think about that, that's 7 on either side. That's the same thinking as here. So 1, 2, 3. Here's Q1. 1, 2, 3 dots, and then Q1. 1, 2, 3 dots. The median, or Q2. 1, 2, 3 dots. There's Q3. 1, 2, 3. So if you think about that, 1, 2, 3, there's a quartile. 1, 2, 3, there's a quartile. It's the median. 1, 2, 3, there's a quartile. 1, 2, 3. So for Martin, the interquartile range is 19 minus 15. It's 4. And that's not a surprise that Martin's interquartile range is more, because his dots are more spread out. That's not a surprise at all. So his is less predictable. Kareem, much more predictable. Now Martin has a faster time, but it's tough to, I actually coach track. I want somebody that I have a very good idea of how they're going to run. Martin might do awesome. He might run a 14-minute, or he might dog it and get a 23-minute. So from a coaching perspective, I would probably pick Kareem to be my runner if I had to pick between the two, because he is much more predictable. I know how he's going to run. Martin, I don't know. He may be awesome or he may be terrible. We don't know. So let's move on to the next little situation. So at the end of the notes file, there's some problems here that we can kind of take a look at. Guided practice 1 and guided practice 2. I'm not going to fully go into detail on these, but kind of talk about them a little bit. So if we look at these, the double dot plot below shows the quiz score. Ooh, below. Wonder why they have that. Shows the quiz scores out of 20 points for 2 different class periods. Compare the centers and variations. If they are both symmetric, then we're going to do mean and mean absolute deviation. If they are both symmetric, and they are. They aren't the same as each other, but each one is symmetric. Exactly the same, nice, goes up and back down, but that makes the mean really easy to do. So the mean for second period is right here. It's the 16. The mean for fifth period is right here. It's 17. That's where the middle of that symmetric arrangement of dots is. So the mean, easy to calculate if they're symmetric. It's the same as that middle or median. So based on that, fifth hour does better on the quiz because 17 is bigger than 16. Okay. Next, mean absolute deviation. Mean absolute deviation. This is the mean. These three dots and these three dots are 1 away. So to do my mean absolute deviation, I'm going to have 1, 2, 3, 4, 5, 6 ones. 1 plus 1 plus 1 plus 1 plus 1 plus 1. Because there are 6 dots 1 away from here. There's 6 of those. And then we have a dot that's 2 away and another dot that's 2 away. So I have 2 of those. And I didn't bother putting 4 zeros for these 4 dots that are at the median or at the mean. But they are dots in the mix. And there's 1, 2, 3, 4, and 4 is 8, and 4 is 12. So I'm going to divide that by 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for what is that? 5, 6. Not very much variation there at all. 5, 6, or what is that? 0.83 with the 3 repeating. And that is for second period. So if I do the same thing for fifth period, I'm expecting a bigger number. Why? Because the dots are more spread out. So I should get a bigger number here. And let's see that we do. So here is my mean. There are 4 dots that are 1 away. These 2 and these 2, 4 dots that are 1 away. So I'm going to have 1 plus 1 plus 1 plus 1. And then we have 4 dots that are 2 away. 2 away. So I'm going to have a 2 plus 2 plus 2 plus 2. And then I have 2 dots, this one and this one, that are 3 away. So 3 and 3. And then I'm going to divide by how many total dots there are. So if I erase all my scribblings here and make sure I'm counting up the dots correctly, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 dots. There's 3 in the middle, 5 and 5, so there's 13 dots. So if I do this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and I get 18 over 13. That doesn't divide nicely, but I don't even have to do the arithmetic to know that it's going to be bigger than 0 point something because it's an improper fraction here. I get 1.38. It says to round to the 10th. So I guess this would be 0.8 and this one would be 1.4 approximately. So based on the mean absolute deviation, this mean absolute deviation is bigger than that one. So fifth hour does a little bit better, but the scores are more spread out. And so that means they're less predictable. There's some kids that did poorly, while others did quite well. More spread out. So in general, they did better slightly, but there's much more variation in how the kids score. So let's look at guided practice number 2, and then we'll be done with this particular lesson. This one will go real quick because they are box plots, so I cannot figure mean or mean absolute deviation. I can only do median and interquartile range. So the median is right here compared to right here. So for Hayes Road, the speed of the cars, the median is 55. For Jefferson Road, the median is 45. Based solely on that, Which one are the cars moving faster on? Well, there we go. Faster cars on Hayes Road. The interquartile range. I don't need to do a bunch of fancy arithmetic. The interquartile range is the length of the box. So from here to here, 50 to 60, the interquartile range for Hayes Road is 10. It's from 50 to 60. For Jefferson Road, the interquartile range is from 40 to 55. So it is 15. So we have, in general, the cars are moving faster on Hayes Road. However, the interquartile range tells us that the cars are moving at a much more varied speed on Jefferson Road. Additionally, we have this crazy person here going between 75 and 80 miles an hour when everybody else is going mostly between 40 and 55. This is not very predictable. So if we were a safety sort of person, which one is there more safe driving going on? This is nice and even though it's faster, everybody's kind of doing the same thing. Here we have some people going 30. We got this crazy person doing like 78, 79 mile an hour. And then everybody else is kind of, but they're more spread out. This means it's more spread out. So on which road were the speeds greater? That's that one. That would be Hayes Road. But if you ask me to make a judgment call, which one is it safer driving on, I would go with Hayes Road is safer because Jefferson Road is crazy. So even though they're going faster, I contend that that would be safer because everybody's doing kind of the same thing. The Jefferson Road, we have some people driving like grandma, and then we have some people like Evel Knievel going crazy. So more spread out, less predictable. I can predict more accurately how people are driving on Hayes Road because of the niceness of that box and whisker plot. So hopefully this helped you out with 10-4.